are starting now a significance test for population means. Okay, so we've already done, we're going to check the conditions for carrying out a test about a population mean. We're going to conduct a one sample t-test about a population mean, and then we're going to construct a confidence interval to draw a conclusion for a two-sided test about a population mean and compare and perform significance tests for paired data, which is actually very cool. So confidence intervals and significance tests for population proportion are based on z values from the standard normal distribution, okay? But inference about a population mean uses a t-distribution with n-1 degrees of freedom, except in rare cases when the population and standard deviation are known. We learned how to construct confidence intervals for population mean in section 8.3. Now we're going to examine details of testing a claim about an unknown parameter value, mu. So the first thing that we have to do is always check for independence, okay? Or I'm sorry, check our conditions. You always want to pay close attention to your sample size, because normally when we're talking about normality, we want to look at a sample size that's greater than or equal to 30, which is the central limit theorem. But if we have a sample size that's less than 15, we want to take a look at the data. And the best way to look at the data is either through a histogram or a box and whisker plot. And we want to make sure there's no outliers and that it's not skewed. So you want to do that with both less than 15, at least 15, and then over 30, we're okay because we're over the central limit theorem amount. And then we also want to check the 10% condition for independence. Okay. Let's see here. Okay, so hopefully you guys have that down. So in summary, basically, if the sample size is small, we should examine the sample data for any obvious departures from normality, okay, such as skewness and outliers and all that fun stuff. Okay, now, when we're doing a test, the test statistic, when we're performing a significance test, we're going to do a calculations assuming that the null hypothesis is true. The test statistic measures how far the sample result diverges from the parameter value specified by the null hypothesis, okay, in standardized units, which is very close to the z-score, okay? So we're going to calculate our test statistic using the statistic minus parameter divided by the standard deviation of the statistic. But understand that because we're doing a sample means, we have a different standard deviation, okay? Because the population standard deviation is usually known, is usually unknown, we use the sample standard deviation in its place. And the resulting test statistic has a standard error of the sample mean in the denominator, okay? When the normal condition is met, the test statistic has a t-distribution with n-minus degrees of freedom. We can use table B or a calculator to find the significance test or the p-value, okay? And we will do these also in class with your calculator, okay? So just don't want to. So our four-step process for significance testing is you want to first state what hypothesis you want to test and at what significance level. You're going to test the true mean of blank in context at a certain significance level. You're going to state the null and alternative hypothesis, and state what the mean represents. It's the true mean, whatever in whatever context it is. So then you're going to name the procedure that you're using. So in this sense, we're using a one sample t-test for means. We're going to check our conditions, and then if our conditions are met, we're going to perform our calculations. Most of the time, if we're given a sample, we can use one of our stats to calculate our mean and standard deviation of the sample, and then use that to help us calculate this test statistic. Then we use the p-value. We can calculate the p-value and then make a conclusion based on the value of the p-value. Now remember, the table B gives a wide range of p-values for a significance, so we can still draw a conclusion from the test in much of the same way as if we had a single probability by comparing the range of possible p-values of our desired significance level. But table B has other limitations. It only includes probabilities for t-distributions with degrees of freedom from 1 to 30, and then skips to 40, 50, 60, 80, and 100 and 1,000. All right, and then the bottom row gives a probability for degrees of freedom with infinity. So if you need degrees, if the needed degrees of freedom isn't provided for in table B, use the next lower degrees of freedom that is available, but that's also why we use our t-statistic. So table B shows probabilities only for positive values of t. So to find a p-value for a negative value of t, we use the symmetry of the t-distributions. Okay? So every road has, at some point, has construction, and in those construction zones we have a lower speed limit. So some police officer decided to calculate what people were driving in these construction zones. And he's thinking, you know what, people are going to be driving over that speed limit. So he's going to test it, and we're going to conclude whether or not we can accept our alternative hypothesis. So we want to test it with a 0.5 significance level, where the mu is the true mean speed of drivers in the 25-mile-per-hour construction zone. So we want to perform a one sample t-test for mu. You want to talk about your conditions. Now, is it normal? Okay. I will remind me to show you guys how to do this. If you need help doing a box plot of this later, just let me know. I could show you how to do this again. But so we only have, I think it's 10 samples. So obviously the central limit theorem does not apply. So we have to graph this and double check and see what it looks like. So when we did a box plot, it's only slightly skewed, so, and it has no outliers, so it's usually safe to use t-procedures. Most of the time, guys, you're going to have to, it's going to meet the expectation of normality, but you have to talk about, if it's less than 30, what you do to make sure that it is okay to use t-procedures, all right? And then we talk about independence. We assume that we've satisfied that 10% rule. Okay. So then we calculate our test statistic and come up with our probability at 0.0069. So since the p-value is less than 0.05, we're going to reject the null hypothesis and say that there's convincing evidence to conclude that the true average speed of drivers in this construction zone is greater than 25 miles per hour. So, given your conclusion in part A, which kind of mistake could you have made? Explain what this mistake means in context. So, since we rejected the null hypothesis, it's possible we made a type 1 error, like we rejected it by mistake. So, if we did make a type 1 error, it's possible that we concluded that the average speed of drivers in this construction zone is greater than 25 miles per hour when it really isn't. Okay? remember, the likelihood of creating a type 1 error is that significance level. So be careful. It's not likely. Okay. So moving on. So here's another one. A college professor suspects that his students at his school are getting less than 8 hours of sleep a night. To test this belief, the professor asks a random sample of 28 students, how much sleep do you get? So there's 28 students. So again, that doesn't meet the central limit theorem requirement. So we're going to have to graph that data. And I did I copied a very lame histogram for you guys, but we can do a histogram in our calculators. If we looked at it, we can see, or you could do a dot plot, which would probably be easier as well, because you could probably do that manually. You can see that there's really no skewness or outliers, and it's relatively normal. Okay, so we have our null hypothesis and our alternative hypothesis, and we're going to perform a one sample t-test for means. Okay, so also it is independent because there's more than most likely he has more than 280 students. Okay, so we calculate the mean using the data of the sample that we got and the standard deviation. That's all done in one var stats. And then we get our t-value, and from there we calculate our p-value. So from there, since our p-value is less than 0.5, we're going to reject the null hypothesis and say that there's convincing evidence to conclude that students at this university get less than 8 hours of sleep. Shocker. Okay. Now let's talk about two-sided significance tests. Go ahead and read this and walk yourself through this. Now what happens is we're saying that our null hypothesis is that it's not equal to 29.5. Okay. They're saying that the mean is 29.5 millimeters and the width of the pretend ice cubes. And we're saying we don't think it is. All right. So we don't think it's either more or less, but it's not going to be that. So we're going to perform a one sample t-test, and just like our two-sided z-test, we're going to multiply those results by 2 because there's two sides where it's not equal to. It could be greater than, it could be less than, and we're going to add those two areas up. Okay, so our p-value ended up being greater than the significance level of 0.05. So we're going to fail to reject the null hypothesis. So there's not convincing evidence to conclude that the true width of plastic ice cubes produced this hour is different from the mean. Okay. All right. A significance test doesn't give us the actual mean, so that's why we do confidence intervals, because we want to actually find at least an interval for the possible population mean. The connection between two-sided tests and confidence intervals is even stronger for means than it was for proportions. That's because both inference methods for means use the standard error of the sampling mean in the calculations. Okay, and we'll put that, I'll show that in a minute. But we're going to do this. A two-sided test at a significance, let's say it's a 95% significance, and we want to do a 5% significance level, so it's the same as a 95% confidence interval. They give similar information about the population parameter, but it's more specific with a confidence interval. Okay, so when the two-sided significant test at that alpha level rejects the null hypothesis, the confidence interval will not contain the hypothesized value. Okay, so since we created a confidence interval that so here we created a confidence interval, a 95% confidence interval for the width of those ice cubes, right? And it's between 29.4. So 29.5 is a plausible value in between these two values that we wrote here. Okay, so that gives us evidence to not reject the null hypothesis. Okay. Okay, so now we're going to talk about paired data. Comparative studies are more convincing than single sample investigations, and for that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations with the same individual or one observation on each of two similar individuals result in paired data. This is a matched pairs design from chapter 4. So when paired data result from measuring the same quantitative variable twice, as in some of our other stuff, if the conditions for inference are met, we can use a one sample T procedures to perform inference about the mean difference, which is mean sub D. These methods are called paired T procedures. So Catherine and Libby decided to see which one was faster. Was the express lane really faster? Okay, and so they really show that they talk about the to the extent to which they go to make sure that this is a random experiment, and then they go ahead and calculate the time. So we want to test the following hypothesis, that at a 0.05 significance level, where the mean difference is greater than, this is our alternative possible thing. So I'm sorry guys, my null hypothesis is that, well, there's no difference between the means of these two things. And our alternative hypothesis is that there is a difference, that there is going to be a positive difference, meaning that the express lane is much faster. So if conditions are met, we're going to perform a paired t-test for the means. We're going to prove that it's random, normal, and again, we had less than 30, so we don't know if the population is approximately normal, and we don't have a large sample size, so we look at the box plot, and even though the box plot is slightly skewed to the right, there's no outliers, so it's reasonable to use T procedures. Okay, now I didn't show you how to do a box plot. I'll show you again. I have shown you this before, but we can go over that in class too. All right. So the next thing we do is check for independence, and then we go ahead and calculate the mean difference between the two. So our null hypothesis is that there's no difference, and our actual value of difference was 42. So we come up with a t statistic, and we come up with a critical value of 0.034. So since the p-value is less than 0.05, we reject the null hypothesis and say that there's convincing evidence that the express lane is faster than the regular lane on average. Okay. So there's a couple things that you need to be careful about. About and using tests wisely. Remember that if you're not a randomly assignment, you can't make inference about cause and effect. Be sure that you always report your degrees of freedom when using your calculator and write it down on your question. So let's talk about using tests wisely. So significance tests are widely used in reporting the results of research in many fields, okay? New drugs require significant evidence of effectiveness and safety. Courts ask about statistical significance in hearing discrimination cases. Marketers want to know whether their new ad campaign is significantly outperforms the old one, and medical researchers want to know whether or not a new therapy performs significantly better. In all these cases, statistical significance is valued because it points to an effect that is unlikely to occur simply by chance. Okay? So carrying out a significance test is easy. Using it is not as simple. So here's some things that you want to keep in mind. When a null hypothesis can be rejected at the usual levels, there's good evidence of a difference, but that difference may be very small, and when large samples are available, even tiny deviations from the null hypothesis could be significant. Don't ignore lack of significance. There's a tendency to infer that there's no difference whenever a p-value fails to attain the usual 5% standard. In some areas of research, small differences that are detectable only with large sample sizes can be of great practical significance. So it really depends on what you're studying, okay? So when planning a study, verify that the test you plan to use has a high probability or power of detecting the difference of the size you hope to find, okay? It's not valid for all sets of data. Badly designed surveys or experiments often produce invalid results. Okay, formal statistical inference can't correct flaws in the design of the study. Each test is valid only in certain circumstances and with properly produced data being very important. Statistical significance ought to mean that you have found a difference at what you're looking for. The reasoning behind statistical significance works well if you decide what difference you're seeking, design a study for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. Okay? All right. Oh, and I wanted to go down to this. Boom, 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 boom. Sorry. That's it. Okay. So, and then I also wrote a note for two-sided tests. Okay, so that is chapter 3. I hope you guys watch this before we start our thing. So I want you guys to make sure that you guys are very comfortable with this, and let me know if you have any other questions. Again, we'll go over some more stuff with the calculator and everything, but I'm looking forward to starting the experiments in class. So talk to you guys later.